Okay, we will be discussing this particular topic. So, electric field at a point on the axis of a uniformly charged loop. So, before we start this article, we need to understand the axis of a loop. Now, axis of loop is any imaginary line which is passing through the center of the loop and perpendicular to the plane of the loop. So, in this case, what we'll do is, we'll consider this to be x-axis, this to be y-axis, and let us consider this to be z-axis. Let's consider a loop which is lying in the yz plane with its center coinciding with the origin, and let plus q be the charge uniformly distributed entirely over the circumference of the loop. This is charge plus q distributed uniformly throughout the circumference of the loop, say of radius a. Now x-axis will act as the axis of the loop and p is the observation point. As I have stated, this x-axis, it is passing through the center of the loop and perpendicular to the plane of the loop, which is the yz plane. Suppose the distance of this observation point p, which is lying on the axis of the loop from the center of the loop, is x. So our objective is to determine the strength of the electric field at point P. So how to proceed is, we'll consider an elementary portion over here. Suppose its length is dl, so the small charge would be dq. Now we'll first find out the electric field due to this charge dq at point P. Now the direction of the electric field from the positive charge is always in the outward direction. So due to this charge dq, the electric field at point P will be directed outwards like this. At this point, the electric field would be in the outward direction. Now this is x, this is a. So the distance of the observation point from the center of this elementary portion would be, suppose r. It would be given by x square plus a square, the square root of this entire term. Now if this is theta, this would be also theta, vertically opposite angles. Now the d, electric field is a vector quantity, right? So it can be resolved in two components using Pareto law of vector addition. So this is the component of electric field which is given by dE cos theta. The other component would be directed towards the negative y-axis, and this would be dE sin theta. And d is the resultant of these two. These two are the adjacent sides of a parallelogram, and the resultant is d, which is given by the diagonal of the parallelogram. Fine. Now similarly, we'll consider a diametrically opposite elementary portion. Diametrically opposite elementary portion. So if this is dq dl, so diametrically opposite, there can be considered to be another element dl having charge of dq. Due to this elementary charge, the electric field at point P would be again along this particular direction, in the outward direction. So it will be again represented by dE. Magnitude will be same due to both these elementary portions at the same observation point. Because charge dq same, the distance of the observation point from any point on the circumference of the loop is constant, and the strength of the electric field is kq by distance square. So it's constant. For both the cases, the electric field is same. Due to the symmetry, this angle will be also theta. So this is also theta, vertically opposite angle. Here d can be still resolved into two components. So this component would be dE cos theta, and this component would be dE sin theta. Now the point to be noted is very, very important point. We have considered two diametrically opposite elementary portions of the loop. The component of the electric field along the positive y-axis and the negative y-axis, they are equal in magnitude. And thus being oppositely directed, these two components will tend to nullify the effect of each other. While on the other hand, the component of the electric field, due to these two elementary charges acting along x-axis is d cos theta, d cos theta. They will supplement each other, they will aid each other. Now point I am making is, there is not only these two elementary portions, there are various elementary portions. Here just for convenience, we have considered only these two diametrically opposite elementary portions. So we can consider several diametrically opposite elementary portions. the component of the electric d sin theta of all those diametrically opposite elementary portions being equal in magnitude and opposite acted will tend to get cancelled out. But the component d cos theta will all act along x-axis. So the net electric field at point P would be given by integration of dE cos theta. This is a very important point to be noted down. It's not given by d cos theta plus d cos theta because this loop is not made up of only these two elementary portions. It is made up of infinite elementary portions. So all the elementary portions which are diametrically opposite to each other, the component of d cos theta due to those elementary portions will be directed along x-axis. So they all will contribute towards the net electric field at point P, and thus it is given by integration of dE cos theta. Right? I'll give you a simple illustration. Now consider this to be YZ plane. This is the loop I have considered. This is the circular uniformly charged loop, and it is considered to be in the YZ plane. This is the YZ plane. This is the center of the loop. This is radius A. Now any imaginary line like this, which is passing through the center of the loop and perpendicular to its plane, this will act as the axis of the loop. I have considered these two elementary portions, which is very clear from this particular diagram. Now consider these two elementary portions. They are also diametrically opposite. These are the two diametrically opposite elementary portions. Now this is the observation point P, right, lying on the axis. Due to this elementary portion, the electric field would be along this direction, outward direction. So it can be resolved into two components, d cos theta, d sin theta. Due to this elementary portion, the electric field at this point would be again directed outwards. Again it can be resolved, one along the positive x-axis, d cos theta, and this d sin theta. Look, d sin theta, due to these two elementary portions, one is directed along this direction, the other is directed in the opposite direction. So the component d sin theta of these two diametrically opposite elementary portions are again equal in magnitude, opposite acted, so they tend to get cancelled out. But the component d cos theta, they are acting along x direction. So they will contribute towards the net electric field at point P. So basically the component of the electric field d sin theta of all the diametrically opposite elementary portions of this loop will get cancelled out in pairs. They won't contribute towards the electric field, right? Now let's evaluate this. So dE is the electric field due to charge dq. dq is considered to be a point charge. Due to a point charge, the strength of the electric field is kq by distance square. So it is k. You can write it as k or 1 over 4 pi epsilon. We are considering it to be placed in a Euro vacuum. Q is dq over u. Distance square. This is the distance of the observation point from dq. This is r. So r is x square plus a square square root. The whole square and square root get cancelled. Cos theta. Cos theta, there is a right angle triangle, base over hypotenuse. So we can write x divided by r. R is x square plus a square. The square root of this. Now dq can be expressed in terms of the radius. How to express it? We'll consider this particular fact. Look, charge is uniformly distributed. Uniformly distributed means we can make use of unitary method. So in the length 2 pi a, this is the circumference of the loop. The net charge uniformly distributed is q. In the unit length of the loop, the charge is q over 2 pi a. Therefore, in the small elementary length dl, the charge is considered to be dq. It will be equal to q by 2 pi a multiplied by dl. So we can substitute this value of dq over here, and then we can solve it. So after substituting the value of dq and taking all the constant terms outside the integration, what we get is 1 over 4 pi epsilon, it's constant. Look, x square plus a square into x square plus a square to the power half. It will be x square plus a square 3 by 2. Then dq, it's equal to 2 pi a, it's constant, it can be taken outside. Net charge is constant, it can be taken outside. X is constant, distance of the observation point from any point on the surface of the loop is same. So all the constant term can be taken outside and we'll be left with integration of dl. Now this integration of dl, it means that the addition of all these elementary portions, they will add up to the total circumference of the loop, which obviously is 2 pi a. So this is 2 pi a divided by 2 pi a, it will get cancelled. So we are left with E net, it's equal to qx divided by 4 pi epsilon x square plus a square to the power 3 by 2. So this is the expression for the electric field at any point on the axis of a uniformly charged loop. This is the magnitude. Now regarding direction, d cos theta, all the components d cos theta are directed on the positive x-axis. So the electric field at point P due to this positively charged, uniformly charged loop is away from the loop, that is towards the positive x direction. So its direction is along the positive x direction, along positive x